Okay, we're going to start off with a discussion of parallelism, and Chris Lamb brought this up. And we're going to go through the scheduled ones that we have on the list, and then if there's other things that people want to talk about, we'll start talking about. This is a discussion, it's an interactive session, so he's going to start off with the issue, and then we'll talk about it.
So, just a little background on me. I'm not a compiler person. I'm not sure anybody here is exactly a compiler person, but I come from a computer architecture background, so I design chips, ISAs, things like that. Specifically, I've been designing many or multi-core chips, lots of parallelism. And recently in my work, I happened to be tasked to do some compiler project management and ended up working with LLVM. And so one of the things that I'm very interested in is, given that my work takes me in a very parallel direction, is how the LLVM community is going to adapt to this era of multi-core general purpose architectures, and also with the adoption by a lot of sort of special purpose silicon companies here. They're probably doing homogeneous, heterogeneous, many core architectures, more than maybe 8 or 16, maybe hundreds, maybe thousands of processors, things like that. So LLVM, as sort of the IR language, doesn't have any representation of concurrency in it natively. And one of the things that this poses a problem if we want to try and do optimizations that take concurrency into account. So I wanted to really open up the discussion to see how the community feels about this, if you've had any thoughts about it. I know a little bit about the discussion that the Java community went through recently in their revision of their memory model to adopt some more, I wouldn't say how to describe it, some more maybe just up-to-date semantics for some of their reordering that they allow in their memory model. So I have some information about that on my laptop, and I've also got a little bit up here. But I wanted to sort of kick off the discussion there with, memory models, load store reordering in light of synchronization and in many parallel threads running on potentially shared memory. Expressing, fork join, concurrency, threads, that kind of stuff in LLVM. What kind of requirements do you feel there are? What kind of interest is there in attacking this kind of problem? Yes?
So one sort of prepackaged set of requirements is the one that will be coming to us from the C++ Standard Committee as they standardize threading.
Mm-hmm.
I don't necessarily want to go into all the details right now, but that's a big pre-existing set of requirements that we pushed on LLVM.
Okay.
Especially since the C committee is considering adopting a threading model basically following C++.
Okay, actually, I didn't know much. Is this the C++ OX stuff? Or is
I believe it's under the umbrella.
Yeah, I don't know a lot about that.
Are you familiar with that? Can you give a brief summary of the requirements?
It's basically being modeled after P threads / Windows threads. Some subset of those is common. And I don't know offhand enough about the memory model that they're designing.
Do you have a timeline for when it will come out?
Well, it's an ISO committee, so it's...
It's OX, so...
It's what?
It's OX, so once it gets to 2010, it's starting to be late.
It's too late.
It's starting to be late.
There is an effort for that to get resolved this year.
So one thing is background. We've had a number of discussions within LLVM about parallelism, and we've come to a couple conclusions. One is that the LLVM part, the IR and down, is really not going to support anything except the raw fundamental primitives that are necessary. Okay. So you're never going to see fork join in LLVM. You might see something like an atomic, read-write modifier, something like that, and those kind of things would be appropriate to add to LLVM, but everything else is higher.
And I kind of agree with that. Looking at the Java memory model, I looked at one of the cookbook pages that's up there about, if you're writing a JVM or something like that, and you want to map this down to one of these, ISAs out there, what are the constructs in the ISA that you need to use to map to the constructs that are in the Java memory model, specifically to do with atomic operations and memory barriers, so things like that. And so there's a lot of choices out there in the ISAs, and really in this aspect, LLVM IR is a lot more like an ISA than sort of the higher level memory model itself. And so I think then there are probably two specific things that we should probably consider. One is atomic operations, and the other is memory barriers. Those could be split up into, you could just have a very generic heavyweight sort of memory barrier, but I think I personally think LLVM could do better than that and have, more fine-grained memory barrier control representation that would allow you to map onto whatever constructs were in the lower level access. Yeah.
So let me ask you this: you're not necessarily going to be successful. It sounds like arguing that what we need are new LLVM instructions that provide threading primitives and whatnot. But how would you argue that LLVM might need a more generalized memoization structure so that you could memoize things like that, so that other passives might be able to take advantage of it, as opposed to embedding it into the LLVM ISA, for example?
Sure. I think that there are places where instructions could have extra attributes or things like that might be efficient at conveying specific information from the higher level. But I think we'd want to choose those pretty judiciously rather than attributing the IR of the wazoo. One thing that I think is also coming is that, at least for my work, fine-grained parallelism, where you have optimizations on code interacting with synchronization at a level where you might want to do scheduling or optimizations, loop unrolling around synchronization, things like that, where it may not be appropriate to just model atomic operations as a function call or something like that, where memory barriers is like an intrinsic function call, where you'd want to actually be able to use alias analysis in conjunction with your synchronization and your memory barrier primitives to try and generate better code. Yeah, Chris?
I have two comments. One with respect to atomic operations. GCC has a bunch of new atomic operation built-ins in one of the recent compilers. I think 4.2 has it, but maybe it's 4.3. So that's it's 14. Okay. So that's a great place to look for prior work, and supporting those transparently is good. The other thing is that the representation of the information doesn't have much to do with how you use it. And so if you have an intrinsic to do a memory barrier, you can still do alias analysis, you can still do anything you want on it. And just like memmove gets optimized and things like that. And so the division over what's an instruction and what's an intrinsic is actually kind of artificial.
So in my mind, it was more what's an instruction or what's an attribute of an existing instruction.
Yeah, that's a good.
So if you look at like the IA64, they have these acquire release barriers that they can put on load and store instructions to provide sort of half memory barriers, which is a bit different than providing a full memory barrier, and allows a little more fine-grained control over what memory accesses can be moved beyond those barriers, and potentially opens up more room for optimization because you're not as constrained. So, what forms do we think that this should take? Do we want to go down that path? Do we want to try to take a very generic sort of memory barrier type approach, memory barrier intrinsic?
Well, I have two comments.
Sure.
One, specifically what you're talking about is memory barrier. So coming from Java, Java memory model does actually have more than just a memory barrier. It has quite a release models, and does actually having that control is really, really useful. I don't know if that's applies to.
So you're saying having the extra control?
Having extra control leads to better and basically better running code in this case. And the other thing also about the intrinsic versus instruction is that sure, inside of the compiler, that difference, is an architectural one. But the key thing is that the people using these are probably going to be not compiler writers, but basically the API writers writing on top of this. And so it's a matter of like, well, if it's already not there, what's the easiest way for them to get into LLVM? Not what's the easiest way for you guys to maintain it or compile the code if there's something that they're not supporting already, if it's an intrinsic versus instruction. I don't know. Which one's easier? Yeah.
I think maybe we do need support for things like thread, fork, and join if you want to do automatic parallelization. So you have to be able to understand how to threads communicate, how the memory model, where this if a thread writes, when it's safe for the other thread to read and things like that. If you're going to pass data from one thread to the other, you you have to add a little bit more than just the atomic operation memory barriers to the language.
Actually, it sort of occurs to me you're going to have to do most of it. A chunk of this is going to have to be done anyway because of the OpenNP support that's in GCC. So a memoization facility that, as stage one is, okay, here are all the thread-based memos that we, stuff in there. And it becomes, you don't want to obviously make a memoization facility become too extensible because that's everything plus the kitchen sink. But it seems like, if you can certainly augment with memos, it might actually be something relatively successful and extensible.
Yeah, I think that might be a really good way to go. For my part, as far as like, by memoization, I assume you mean sort of attribution of the IR, or?
Yeah.
Okay.
Yeah. Here's my PC, memo, instruction stream. And then, of course, the backends can do with it what they want.
So we've actually had this argument in LLVM before, and we've got a class called annotation.
Right.
And we're trying to get rid of it.
Well, yeah, but you could consider alignment information, although the source of the annotations also found.
Right, but the point is that they're not right? They're actually.
But that's a terminology issue. So calling something an annotation, and it really depends on how it's implemented. And we don't want to support arbitrary annotations of random crap on the IR,
which is where
no offense to people who want to put random crap on the IR. But
so as long as it's specific, then we can attach those attributes to particular things. The thing is, if it's just a random thing and people dump random information in there, who does anything with it? None of the backends are going to end up supporting it because it's random. So
well,
it needs
you
to be
obviously
very,
have to make them fairly well defined. I mean,
right.
I'm not saying just put arbitrary crap in there because.
So what I'm saying is that if you're going to make them well defined, then you might as well make them, very real attributes of the IR.
Sure.
So,
but you have to start with an extensible attribution structure to begin with, which sort of exists, but.
I mean, would you consider the bit code format to be sort of extensible as you would extend attribution? Extending an opcode or extending an instruction in bit code format is pretty extensible from what I understand, right? So the way when I was doing the alignment stuff, which is adding basically new information to the load and store stuff, I was basically adding information to an existing opcode. If one considers that extensibility, then yeah, I'd say that the entire IR is pretty extensible, right?
That's the way I see it being done.
So I think specifically, looking from the Java memory model, there were 4 things that I was thinking about, and that's the 4 types of memory barriers that they sort of require you to map somehow onto your ISA, and that's the load, store load, and store memory barriers. The IA64 acquire release stuff basically provides that, but grouped into 2, which are a little bit more strict. And probably should have a discussion about what's the minimum set we want to support that really makes sense, how that would interact with any sort of atomic primitive that we want to put in the language or attribute onto existing instructions. But that was basically my starting point was, if we wanted to support the memory model that Java has come to, we need to have something like this in the IR to represent either through intrinsics or through attributes on existing instructions. We'd have to have some way to represent these memory barriers to actually generate proper code.
I was just going to point you in the direction of some work that SGI did with the MIPS chip, and they had a thing they called nanothreads, which were more primitive level, closer to the hardware architecture of which pthreads then resided on top of. But the direction that they were moving in sounds very much like what you're talking about in terms of how can you support a threaded environment in a more efficient way.
Okay.
One comment I'll make is just adding memory barriers to LLVM is actually going to be more tricky than it sounds because different processors have different semantics for memory barriers. So some of them order all writes before the barrier with all memory operations after, some order reads and writes with all operations after. We actually have all possible combinations that exist out there.
Yeah, so I mean, certainly it wouldn't just be as easy as adding the attributes to the syntax. You'd have to make the optimization passes, respect them, and you'd have to get the backends to lower them onto the correct memory barrier operations for that specific target. The cookbook for the Java memory model, I think, for that would be a great place because they've had to do it for all their JVMs and all these targets, and they go through the matrix of, well, these are the instructions you can use for these memory barriers, and these are the special cases you have to watch out on these architectures and things like that. But
yeah, except that the front end we're using is eventually going to have OpenMP in it, which basically means that the Java stuff is well nigh useless. So you have to then sort of figure out, okay, what's the best merge between the two.
well, specifically with the memory barrier stuff, the Java stuff, from what I understand, is pretty much strictly more conservative than what C and C++ implement right now. I don't know about C++ OX.
And ideally, we find the common set of primitives that are useful for less implementation.
Yeah.
So the idea,
something that's supportable.
the idea I had was sort of going for what ISAs you implement because we've been able to map C and Java down onto these ISAs. They have some sort of subset that's at least minimally functional for these kind of queries. So.
Yeah, well, I don't think the answer is to reach a solution right now, but it's to raise the issue, and now lots of people are thinking about it, and we can discuss it over breaks. And
Absolutely.
Yeah, it sounds like someone needs to take the lead and just figure out what all the application, different styles of multi-threading are, and then work with the target support and sort of synthesize what we need in the middle for LLVM.
One thing that just think about many architectures having different memory barriers. It seems like x86, where if you write and then read, it's always valid. There is no memory barrier. You could argue that the code generation could just not emit anything.
Correct.
But it would be interesting also that previous optimizations use the fact that there is no memory barrier to do the correct optimization. So it looks like it should be something that targets that have represented higher level optimization can look down and see for which architecture is going on, which is kind of unfortunate.
I think one of the things for potentially representing these barriers in the language is that it sort of happens to some extent at target lower end time or when you lower onto the back end, which of these become no ops or which of them actually have to be code generated into barriers themselves on that. Any other discussion points? If not, we'll take up more discussion on the list.